completed his PhD from the Chennai Mathematical Institute, better known as CMI to most of us. His areas of interest include program verification, program analysis, and specification and analysis of real-time and hybrid systems. Today, he'll be talking about Turing's contributions to computing and computability. Good morning, sir. We're delighted to have you here with us today.
Good morning, and thank you for the invitation. How much time do I have?
So you can take up till 45 minutes to an hour. It's up to you.
Okay, and so I'll try to wind up within that. Okay, so let me just share my screen. Okay, so good morning, everyone, and it's a pleasure to interact with you all in this talk and in the seminar. Unfortunately, I may not be able to attend one of the remaining talks, which seem very interesting because I'm traveling right now. Okay, so I'm going to tell you a bit about Turing's contributions in the context of computability and logic, which were some very exciting times in which Turing worked and contributed many of the basic ideas which live with us today. So many of these topics that I'm going to talk about are there are some courses in the institute, and some of them which all will be doing later. So I'll tell you all a bit more about that towards the end. So as you all know, Alan Turing was he had a very short life in the sense that he passed away when he was just 42 years old, but had an amazing amount of contributions and impact in computer science in those short years. He had a difficult life in many ways, and also there was a strong connection to India because his father was in the Indian Civil Service and posted to India several times. Many of his grandfathers were in the Madras Railways and things like that. So there's a strong connection of his family with India, both on his mother and father's side. And he made several contributions to computer science, including artificial intelligence, and he was a key, cryptanalyst during the Second World War, and his work might have helped the Allies win that war. Biological computation. Okay, but we are going to be focusing on his work on computability and logic, which is probably, I think, the work that he is best known for, and for which he's, I guess, recognized the most in computer science. Okay, so he gave us this, I guess his main contribution was that he gave us a widely acceptable notion of computability. And his model of computation has inspired the modern computers that are in use today. Okay, so let's get into some of the details, and please feel free to stop me if you all have any questions or if anything is not clear. You can just look at things at a informal, high level without getting into the details. Okay, so what is a computable function? That is the basic problem that Turing addressed. Okay, so one could think of a function. Let's consider functions from natural numbers to natural numbers. Okay, and now when do we say that some function is computable? Okay, so what do you guys think? Can you all tell me what you all think of how would be so? The basic idea would be something very similar to what we have today, where we call an algorithm or a program that one could write to compute a function. Okay, but do you guys have any ideas? What would you say? Are you all able to hear me? Or maybe I've got disconnected.
We can hear you, Professor.
Okay. Okay, so let me go ahead. Okay, so let's say that a function is, I'll say that a function is computable if you can give me like a finite recipe to compute the value of f of n, okay, for any input n. Okay, and so this notion of what is this finite recipe, what is this finiteistic means of presenting the evidence that f is computable. That is the thing that really has to be pinned down. And if you go back a decade back when Turing and others were working, this was completely uncharted territory, and people really didn't know how to formalize this notion. Okay, so you could think of a recipe for just like we have like a cooking recipe. You take so much of this, you take so much of this, and then you apply some steps. If this is not done, you go back to the step, repeat it, right? And so, for example, you could think of a small recipe or an algorithm to compute the sum of two numbers, right? So you write, let's say the numbers are given to you in the decimal digit representation, and you could write a program which computes the sum and carry for each digit starting from the right. Okay, this is similar to the way we normally do addition in school. Okay, and an important thing about this recipe to say that the function that it is computing is actually computable is that this recipe should eventually terminate on every input that you started on. Okay, so if I'm adding two numbers, then whatever numbers I'm given, this recipe should eventually terminate and give me an answer. Okay, so that's the key thing to saying that something is computable. I want a finite representation, finite means of representing the device that computes this function. Okay, it could be a recipe, it could be an algorithm, it could be some kind of a machine. Okay, and this machine should always terminate and give an answer for it, no matter what input I give it. Okay, so that was kind of informally the notion of a computable function. And so, for example, you could take some few examples like this. So, for example, if I say that consider the function which maps every natural number n to 2 power n. Okay, so is this a computable function? Would you all say it is computable?
Professor,
Yeah,
the
yeah.
mics
So,
have been disabled for all the participants, so no one will be able to reply to you.
okay, why is that? I mean,
Please
they should
carry
be
on.
able to interact.
Give us a few minutes, we'll get on that.
Yeah, okay. So
Until then, please carry on.
yeah. In the meanwhile, I'll continue. Yeah.
Been granted as of now.
Sorry?
The permissions have been granted for mic.
Oh, okay. Yeah, so please tell me, what do you all think? Is this first function that I've written, is it computable? Intuitively, what do you say that it's computable? 2 power n?
Yes, I mean, if you take multiply by 2 in every step, n steps.
Right, okay. Yeah, thanks, Maitri. Right, so I could, if you give me a number like 17, I'll and I'll multiply it by itself 17 times. Okay, so I'll keep the first product, and then I'll again multiply by 2, and I'll keep doing this. Right, and maybe I'll keep a count to know how many times I've multiplied. And once that count equals the given number, which is 17, then I'll stop and return the number that I have. Okay, so that's computable. Okay, what about this second function, okay, which says that given a number n, it returns just 0 or 1, okay, very simple output values, but it says you should return 1 if there are 3 other natural numbers, x, y, and z. If there are 3 natural numbers, x, y, and z, such that x to the n plus y to the n should be equal to z to the n. Right? So, for example, if I give you 2, then your answer should be 1, right? Because I can take x to be 2, y to be 3. What would it be? Maybe I need
3, 4, and 5.
3, 4, and 5. Okay, so 9, 16, and 25, right? Okay, so if I give you input n as 2, then you should give me 1. Okay, and maybe there are other numbers for which you should give me 0. Okay, so is this function computable?
No, because you'll have to try all triplets.
Right, but maybe I have a clever way, right? For example, if I knew, so this is related to Fermat's last theorem, and if I knew that, that is true, then maybe I can just always output 1. Maybe. So we don't know. Maybe there's a clever way to figure this out, and therefore there is also an algorithm that will do this. Okay, so it gets a little more difficult if you look at, because it's a very expressive, functions can capture, just functions from natural numbers can capture a lot of things. Right? So for example, this other one is, I think I called it something else, but okay, the other one, for example, this last one takes the encoding of a machine, okay, as a number. Okay, and it should output 1 if the machine represented by the number is, has a halting computation. Okay, that should output 0. Okay, and so these kind of functions make it, for example, maybe the first is definitely computable, and maybe the last one is not computable. Okay, but how does one, how does one say that something is not computable, and why should one even, worry about why, whether something is computable or not? Okay, but before we come to that, are there any uncomputable functions that you all know of? Or, I mean, do there exist uncomputable functions? So let me see what else is there. Okay, Yukta, are you there?
Yes, sir.
Yes. So do you think there are, so roughly is the idea of computable functions clear to you?
Yes, sir.
Okay. If so, what do you think, are there functions which are not computable, or is every function computable?
So I can't think of an example of an uncomputable function as of now.
Right. Yeah, it's a difficult thing to do that, yeah. And it's difficult to, and even great mathematicians like Hilbert were not able to pin this down. Okay, but if one does a simple, I don't know, in your discrete math course, well, you all have done, these kind of arguments about counting. Okay, so if you, so the answer is that actually almost all the functions are uncomputable. Okay, there are very few functions, even though there are infinitely many, but there are uncountably many. I mean, the ones that are computable are only, only countably many, whereas the ones which are uncomputable are uncountably many. So a large part of this, if this Venn diagram represents, the universe, the set of all possible functions from natural numbers to natural numbers, then a very small dot in this diagram is the class of functions that are computable. Okay, and it's very easy to see that because if I say that a computable function must have a kind of finite recipe associated with it, which is the witness or which is evidence for the fact that this function is computable. Okay, then that recipe is essentially a finite string. Okay, it could be a program, it could be an algorithm, maybe a Turing machine, right? But it's representable as a finite string. Right? Just think of a program. I just write down all the characters in my program as a long string. Okay, so every object that witnesses a computable function is essentially a finite string. Okay, and how many finite strings are there? How many finite strings are there over a finite alphabet? Okay, there are only there are only countably many of them, right? How do I count out strings? Can one of you tell me? So you know when a set is countable? Yeah, sorry, go ahead.
So we can give an ordering like how we give for binary strings or like decimal strings.
Okay, who's this speaking?
I'm Shishir.
Shishir, okay, yeah, Shishir, go ahead.
So we can give an ordering like how we give for decimal 1, 2, 3, 4, 5, 6, 7, 8, then 10, 11, 12, like that.
Right. So basically, a set is enumerable or countable. If I can, just write it, I can give a way of, associating with every natural number. What is the zeroth? What is the zeroth element of this set? What is the first element? What is the second element? What is the third? Right, and there can be repetitions. Maybe the first and 17th element are both the same. Right, but I just have this list. But what is guaranteed is that every element of the set definitely occurs in this list. Okay, and I need not even have a constructive way of producing the list, but I can just tell you that look, this list exists. Right, so then you say that the set is countable. Okay, so it's easy to see that the set of all these these finite recipes that we have is a countable set, because essentially I can represent them as a finite string, right, and I can count the set of finite strings over a finite alphabet in a very simple way. I mean, I can't use the dictionary ordering, but we can use something which is called lexicographic ordering. Okay, so I list all the strings of length 0, then list all the strings of length 1, and I list all the strings of length 2, and so on. Okay, that way I'm going to cover all the possible strings in this enumeration. Okay, so the set of that implies that the set of countable computable functions is a finite set. I mean, is a countable set. Okay, so there are not too many of them. They're countably infinite, right, at most, right? But if you take the set of all functions, how many functions are there from natural numbers to natural numbers? Okay, there are infinitely many, but they're uncountably infinite, right? So I don't know whether you all have done this in your discrete math course. Okay, but here is an argument for why this must be an uncountably infinite set, right? So suppose I claimed that the set of functions from natural numbers to natural numbers is enumerable, is countable. Okay, then I have some listing. I can say this is function f0, f1, f2, f3, and so on. Okay, this is the first. These are the functions in my list. Okay, and I can write down each of these functions as a map from natural numbers 0, 1, 2, 3, 4, 5, right, which is there in that column, right, and maybe f0 maps everything to 0, so that's the first function. And f1 maps everything to +1, okay, so that's the second function, and so on. Okay, so suppose I claim to you that that the set of all functions from natural numbers to natural numbers is countable, then you will say, okay, then you must, I can write down your, I can write down your enumeration like this, as a table like this, right? And now what you can do is you'll construct a new function g, okay, which differs from all these functions, f0, f1, f2, f3, in at least one position, right? In the sense that there's at least one natural number which differs on who the image, these functions give a different value. Okay, and you do that by this diagonalization technique, which was done by Cantor, maybe to show, for example, that set of real numbers is not countable. Okay, so the basic idea is that you look at this diagonal element and you say on 0, this f0 is giving 0, so I'll give, let's say, 0 plus 1. Okay, so g will give 1. On 1, f1 is giving 2. Okay, so g will give 3, 2 plus 1. Right, on 2, f2 is giving 8, so g will give 8 plus 1, 9. Okay, and similarly F3 on 3 is giving 0, so G will give 1. Right, so you can see that this function G, differs from each function Fi in the ith on what it says on the ith input, on the input I. Okay, so therefore this function G doesn't occur anywhere in, right, so therefore I have not covered all the functions from natural numbers to natural numbers. Right, so that is your argument, which will tell me that, look, what you're claiming is not possible. Okay, and therefore the set of, this class of all functions is not countable. Okay, so it's uncountably infinite. Okay, so that immediately tells us that there are a huge number of uncomputable functions. Okay, no matter what your definition of computability is. Okay, do you all have any questions on that?
So how do you show that there are countably many computable functions?
Right, because, so, okay, let's say, suppose my definition of a computable function was that you have a C program to compute it. Okay, so if you, so this is my definition, let's say, of a computable function. Okay, now, how many computable functions can there be? There can be at most as many as there are C programs.
Yeah.
Right? Because for every computable function, you need you at least one C program. Maybe 2 C programs compute the same function, but you need at least one. Okay, so the number of computable functions is not more than the number of C programs. Right? And a C program is just a finite string, right, over a finite alphabet. Okay, so if you think about it, you can enumerate finite strings, the set of all finite strings over a finite alphabet in the so-called lexicographic ordering. It's slightly different from the dictionary ordering, but as I said, for each you enumerate in increasing lengths, and within a length, it's a finite number of. So there you can use dictionary ordering if you want.
Yeah.
Okay, but every string will be enumerated in this ordering, right? So basically because the set of programs, C programs, is enumerable. So therefore, the set of computable functions is also enumerable.
Yes, sir.
Right. So remember that in enumeration, you're allowed to have repetition. That's not a problem. Right. So the same C program, the same function can appear multiple times because it's computed by 3 different C programs. Okay. Anyway. Okay. So why should we worry about a function being computable or not? Right? What is a big deal? Okay, maybe it's computable, maybe it's not. Why should I break my head over it? Okay, so one thing is that it's very often, even in when you're doing, trying to solve a problem, write a program to implement solve some problem, try to come up with an algorithm to solve a problem. It may the problem may be difficult. Maybe there is no solution to it. No matter how hard you try, you cannot come up with an algorithm which will correctly solve that problem. Okay, and how do you know that? Right. So if you have a way of showing that a problem is undecidable, unsolvable or uncomputable, right? Then you can, that settles the issue. You don't need to keep trying to find an algorithm to do it. Okay, so there are many problems, that one comes across which are kind of on this, you don't know which side they lie. Maybe it's uncomputable, maybe it's computable with a high complexity, but we don't know. And this technique of which Turing and others pioneered helps us to show, many problems that they are undecidable and forget about trying to find an algorithm to solve it. Okay, but so in the 1930s, why was this a very what was the burning issue there in the 1930s in Turing's time? Okay, so let me give you a bit of background about that. And it's a very interesting part of mathematics and logic. This interesting time in the history of mathematics and logic. some great results, and it was also like the birth of computer science. That's when Turing's work kind of maybe gave a foundation for computer science. Okay, so I've just tried to give a kind of timeline and a kind of genealogy graph to show the main dramatis persona in this story. Okay, so one could think of it as starting with David Hilbert, even though these ideas had gone back to the time of German logicians Leibniz and Frege and others, maybe a century before that. Okay, but around 1928, David Hilbert, so you all had this very interesting seminars on paradoxes that Professor Pandurangan put you all in touch with. And you would have realized that there were a lot of these inconsistencies in mathematics, like Bertrand Russell's paradox about he constructs a set and then asks does some other set belong to that set or not, or maybe does the set itself belong to itself or not, right? And the answer is you can't say yes, you can't say no, right? So that's a bad thing. It means that your foundations of mathematics are inconsistent in that sense. Okay, so Hilbert's so-called formalist program was to try and say that, look, I'm going to put mathematics on a firm, logical foundation. Okay, I will give a proof system, like a set of axioms and proof steps, proof rules, right? And I will only believe things that are proved using this proof system, right? So I won't, if someone has a theorem in mathematics, they better use this proof system to, formally establish that the theorem holds. Okay, so that was roughly what his plan was. And in 1928, along with Wilhelm Ackermann, they wrote this. I have that here. Okay, this basically Principles of Mathematical Logic. The translation in English, it says. Okay, and right, so the basic. I'll explain some of these things a little in the next few slides. Okay, but the basic question was there were several basic questions. The first one was, can you give me a proof system for first order logic? Okay, so you'll see what that means, but it's essentially like you're not interpreting first order logic in a particular domain, like arithmetic, natural numbers, integers, or reals, right? But over general structures. Okay, and so there's a notion of validity there, or logical consequence there. If I give you a set of axioms, capital X, okay, the question is, does this this formula phi follow as a logical consequence of X, in the sense that if I take any model, in which all the formulas in X are satisfied, then is it also the case that phi is also satisfied in those models? Right? So you can think of, for example, X being the axioms of groups. The three axioms that we have for a group. So there's basically a domain in a group, and there's an operation. Have you all studied group theory already? I guess you all must have done that, no? In algebra?
We have seen fields, but not groups.
Okay, fine. So anyway, so there's a binary operation on a set, and it should follow, the binary operation should be associative, and there should be there should be an identity element in the sense that if I operate any element with that identity element, I get back that element. Okay, and maybe they should exist in inverse for every element. There should be exist another element such that when I take the operation of these two elements, I get back the identity element. Okay, so those are the axioms of groups, right? And then anything that is a logical consequence of these three axioms is essentially your whole of group theory, right? All the theorems that you use, that you study, are essentially the logical consequences of these three axioms, right? So it was so basically Hilbert and Ackermann's question was: can you, given a finite set of constraints, given a finite set of axioms X, okay, can you tell me whether phi is a logical consequence of this set or not? Okay, so that was what we call this Entscheidungs problem, or the kind of decision problem in German. Okay, can you decide logical consequence? Right? Given a statement like every element has a left inverse, is it true or in a structure that has that satisfies the axiom of groups? It's essentially is something a theorem of groups. Okay, so this was really Hilbert's program kind of rested on these questions, and he very firmly believed that all these answers had a positive. All these questions had a positive answer. That there should be a sound and complete proof system for first order logic. There should be a decision procedure, an algorithm that will answer the Entscheidungs problem. Right, and he also asked: is there a is there an axiomatization for arithmetic? Let's say the set of natural numbers, addition and multiplication, right? The usual numbers that we deal with, operations that we deal with. Is there a axiomatization of, just like we have for groups, is there an axiomatization for arithmetic? Okay, so you can see that the consequences of this, of having answers, positive answers to these questions, would be, momentous, because, for example, if I really wanted to know what are all the theorems in groups, I could just take this proof system that is there, and just generate longer and longer proofs. Just keep doing that. I'll just write a program and I'll start a machine and, just let it keep running. And each time it prints out something, I have a proof. I have a theorem in groups. Right? Similarly, I could have theorems in number theory, just printed out, generated by a computer. Right? And every theorem that is there in number theory is guaranteed to be output at some point or the other by this machine. So very it would kind of trivialize the whole of mathematics if this was true. Okay, so going back to this picture here, so in a nutshell, this is where the work of Gödel came in. So Hilbert's questions were posed in around 1928, and in 1929, Kurt Gödel, who was a PhD student at that time, in his PhD thesis, he showed that first order logic is indeed complete. He gave a sound and complete proof system for first order logic, right? And a couple of years later, he showed that for first order arithmetic, okay, there is no sound and complete proof system. Okay, so no matter how hard you try, there cannot exist a sound and complete proof system. So that kind of put an end to Hilbert's formulas program, because if I cannot even guarantee that I can derive every theorem that is true in arithmetic, forget about the larger mathematics, parts of mathematics. Okay, so that was around 1931. Probably the most, if you think about the way he proved it, probably the greatest intellectual achievements of humankind was there in Gödel's work. I mean, at least in this last century. Okay, then if we, so that was in Germany and Austria and a little later in Princeton, Alonzo Church, and he had he had many students, including Stephen Kleene, Rosser, Scott, and Rabin. These are all well-known names in computer science today. And also Alan Turing, who was earlier did his master's and bachelor's at Cambridge in the UK. And later he came and joined Alonzo Church for a PhD, 1938 or sometime around that time. Okay, but essentially Alonzo Church showed in 1936 that this inheritance problem was unsolvable. Okay, remember the inheritance problem was given a set of axioms and given a formula. You want to know, is this formula a logical consequence of that set of axioms? And Turing also came up with a proof for just a little later. In fact, I think he had independently come up with his own notion of what is computable in terms of this Turing machine, and he'd given a proof that this inheritance problem was undecidable around the same time, but it was published a little later than Church and Kleene's work. Okay, so that's a little bit of background. So let's. Okay, I'm going to skip this introduction to logic a bit. Maybe I've just told you all already roughly what it looks like and what the issues are. Okay, so let's go quickly to Turing's let me try to wind up in the next 5 or 10 minutes. So Turing's right. So coming back to the problem, right? Remember that this notion of, if I want to show that some problem is computable, some question is computable, like the inheritance problem, I need to have a notion of, I mean, either I come up with a technique and it's come up with an algorithm and it's okay with everyone to see that, okay, fine, this this is I believe that this is computing the right, computing this function correctly, right? But the other thing was if I want to show that it's not computable, right, I need to have a very concrete notion of what it means to be computable. Okay, and that is what Turing proposed, and probably his most lasting contribution to computer science. Right? Even though there were many other notions that were already present. For example, Church used this notion of lambda calculus to represent numbers, and his notion of computation is essentially doing this reduction on lambda terms. Right, and when you reach a normal form, that is a form in which this lambda expression cannot be further reduced, right? That is like your output or the output of the algorithm. And so he had that notion of computability prior to what Turing came up with. Okay, but nevertheless, Turing's notion was probably the most compelling and the easiest for people to appreciate that this really does capture the notion of computability. Okay, so what was Turing's notion? So roughly, he's given a machine. So think of it like a conceptual machine that runs has a long tape, and this machine has a head which can read one cell of the tape at a time. Okay, it can only very simple things it can do. It can read the cell currently that it is reading. Like for example, here the machine is reading this symbol A on this cell. Okay, and the machine has a state. It's a finite number of what Turing called configurations, or what we call states now, control states. Okay, and it can, in any state, it can, based on the symbol it is reading and the state that it is in, it can choose to rewrite that symbol by something, maybe rewrite A by a B, okay, and move left or right one step. Right? So those are the basic operations that this Turing machine can do, right? And what was the notion of computability? So you'll say that so suppose I'll say that a function f is computable, right? If you started with, let's say you give me the number in decimal or binary or something, you write down the digits of the number on the tape, followed by a hash symbol. Okay, let's say there are, for example, if you want to add two numbers, then you're given two inputs, let's say n cross n to n, right? So given 10, and then you're given a hash, and then you're given 27, and then you're given a whole sequence of blanks. So this tape is, there's no limit to how much you can read or write on the tape. It's an infinite sequence. So just to say that your kind of memory is unbounded, you can write whatever you want. Of course, at any time you can only utilize a finite amount of space, but there's no bound, there's no limit on how much you can use. Okay, so the machine starts off in a configuration like this, runs for some time up and down, changes things on the tape, right? Scans up and down, then finally it gets into a special halt state. Okay, and then you read the output read what is there on the tape, right? And you take that to be the output of the function on the given input. Okay, so if I'm adding two numbers, if the machine is adding two numbers, then you would expect to see 37 followed by a sequence of blanks on the tape. Okay, so this was Turing's. I mean, I've given a very high-level view of it, but this is essentially what Turing's automatic machine, what he called an automatic machine. Right? You just started off, and then it runs chuck, 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 going left, right, doing a whole lot of things. Finally, gets into a halt state, and then you read the contents of the tape, and that is your output. Okay, and he showed that many common functions were can actually be, you can write Turing machines functions that are commonly considered to be computable. You can also write Turing machines to compute those. Right? Anything that has a Turing machine to compute it is clearly computable, because it's giving you of course, once again, the caveat is that the machine should halt on every input. Whatever input I give it, let it run for as long as it wants, but it must eventually get into its halt state. Okay, so that's like a halting machine. Not every Turing machine needs to halt. Okay, but if you say that the function is computable, then you must give me a Turing machine which computes that function in this sense and which halts on every input. Okay, and one can represent a Turing machine as a string. For example, so a Turing machine has only some number of components, right? You must tell me what is the number of states in the Turing machine, what is the alphabet of the Turing machine, okay, and then what are the moves of the Turing machine. So I can just encode this as a binary string like this. For example, this 3-state Turing machine, I can write down saying that it has 3 states. Here, 3 zeros representing 3 states. Then I'll put a 1 as a separator. Then maybe 4. It has 4 alphabet symbols. You put another 1 as a separator, right? So on. And these are the transitions. Each, the move. If I'm in state S and I see a blank symbol, then replace it by a blank symbol and move right. Okay, so these are the moves of this Turing machine, which again you can write down as a finite sequence. Okay, so the long and short is that for every machine I can write it has a simple description as like a binary string. Okay, and now because of that you can now give a Turing machine which has the self-referential property. Once again, you all saw in the paradox seminars that the self-referentiality was a very kind of important ingredient of getting into a paradox. Okay, and that is also the thing here which Turing exploited to show that you get this unsolvability or uncomputable problems. Okay, so given a Turing machine, you can define a Turing machine what Turing called a universal Turing machine, okay, which given the description of a Turing machine as input, and maybe another string giving the input itself to that machine. Okay, it would simulate the given machine on that input, right, and tell you whether what is the output of that machine or whether it halts or not. Okay, so that's the universal Turing machine. Okay, and Turing basically said that this problem of if I give you a string representing the encoding of a Turing machine, right, you cannot output 0 or 1 depending on whether this Turing machine halts on its given input or not, right? Okay, so this is the function. Given a binary string, think of it as a number and binary, represented in binary. Okay, and I want to output 0 or 1 depending on whether the Turing machine represented by this number and the number also has the input of the Turing machine, and whether this Turing machine halts on the given input or not. Okay, and so this problem Turing showed is not computable, and his basic idea was very similar to the diagonalization argument that we saw earlier. Okay, he said that if you can compute what the particular Turing machine does on a particular input, okay, then I can essentially flip the diagonal in this table, right, and I'll produce a machine that doesn't that behaves differently from all the Turing machines possible, right? So therefore you cannot compute compute the whether a given Turing machine halts on a given input or not. Okay, so I'll skip the details of this, but it's essentially the idea is very similar to the diagonalization argument that we saw earlier. Okay, so he constructs this new Turing machine N, which essentially flips the diagonal in this, and this machine, right, differs from the behavior of all the machines in this listing. So therefore, there can be no such Turing machine N. Okay, so I think I'm pretty much running out of time, but okay, so I just gave you all a brief overview of Turing's contributions, right, and in the context of computability and logic. Okay, and as you can see, maybe one question you might ask is, I mean, why is Turing considered the father of computer science? And why name, for example, the ACM-Turing Award? Why name the top prize in computer science after Turing, right? And why not, for example, Gödel, right? Or why not Church or Kleene? Okay, so I mean, it's a question which comes to mind because you can see that in terms of the the breakthroughs that were achieved, maybe Gödel achieved those breakthroughs in the early 1930s, right? Maybe the undecidability proof was also done by Church, maybe independent of Turing's work, but published a little earlier than what Turing did. Okay, so why name computing's top prize after him? And I think the main answer is that, firstly, the notion of computability that he gave was, the most was one that was the most compelling, right? And it was widely adopted, and people could understand it. Secondly, it inspired the design of today's computers. What is popularly called the von Neumann architecture, where a program is stored in the memory of a computer, and you execute it. Is very similar to Turing's ideas of a universal Turing machine, and von Neumann himself acknowledged that he was influenced because Turing was also there at Princeton around that time, right. And I think the most striking fact is that if you look at the computer science curriculum, especially the theory curriculum today, it very strongly mirrors Turing's concepts and the notation that he uses if you go back and look at his 1936 paper on this, on computable numbers and this solution to the Entscheidungs problem. Very many textbooks and automata or complexity theory use very similar, notation. They're all based on the Turing machine. Computability is based on whether Turing machine can compute something. Complexity, how hard is a problem to solve, is based on how much time a Turing machine would take to solve it, right? Or how much space a Turing machine would take to solve it, in terms of the size of the input. Right? So a lot of, so that part is really striking, and it shows how much Turing has, influenced modern computer science. Okay, so I'll stop with that. Maybe I'll just quickly point out to you that for those of you all who are interested, there are many opportunities to learn more about this in your program, in your BTech and BS programs. So in your 4th semester, the BTech students all will be doing this course, which I will teach you on automata and computability, and many of these things, Turing machines and Gödel's incompleteness argument, you will see in that. And I also teach a course on mathematical logic and theorem proving, where we do a lot of Gödel's, for example, Gödel's first completeness of first order logic. So very kind of closely interrelated, these two topics and courses are. Also, Professor Siddharth Gadgil from the math department teaches a course which does a bit of logic, proof theory, and type systems. So that's also closely related. And then we also teach a course on program analysis, which uses a lot of lambda calculus that I mentioned, Church and Kleene had come up with. A bit of the course focuses on lambda calculus. Right. So, okay. So thanks for listening, and looking forward to having you all interacting with you all in these courses later. Thank you.
Thank you very much, Professor.